Hey, I'll just give me just a minute. I had to come outside today. We got a repair guy coming by from. If you remember, a couple weeks I had a leak, a water leak, and he's repairing some of the damage. So I had to set up outside. Just a second. Came real close to just canceling. Mm. Oh, um, okay. There we go. Okay. Alrighty then. Oops. Okay. So we talked about complete equilibrium, total equilibrium, right? And that just means that the sum of the torques is equal to zero, sum of the forces is equal to zero. Today we are going to look at orbital angular momentum. So this is the angular momentum of one body going around another body. Okay, so like the moon and the Earth, right? That's common, or the Earth and the sun, anything like that. Where something is in orbit around something else. So this would also apply to any satellites or anything like that. So we know that tau is equal to R cross of the sum of the forces. All right. We also know that the sum of the forces is equal to, it's really just the sum of this, but I'm just going to write dp over dt. All right, so we can play in this, we can replace or substitute in for that sum of the forces in our equation for torque. So we're going to get R cross dp dt, or the derivative of p with respect to t. Okay. And we can take in that position vector because, again, position is also going to change with time. So we're going to have ddt of R cross p. And this right here, this is our orbital angular momentum. Okay. All right. And more formally, we write it as L equal to cat. R cross P. This cat just shit a bunch of hair and fur into my face. Okay, so that's the formal equation. Is there a question? Okay. Where L is orbital angular momentum. All right. The units are joule seconds or the kilogram meter squared per second squared. Right. And so what's going on here is just like what I said. Let's say we have the Earth, and then we have the moon, moon. It's kind of hard to. The moon, and the moon is orbiting, right? It's orbiting around the Earth, and so it's going to be given some. It's got some tangential velocity there, v velocity, and we've got an angle between the velocity and the position vector, which I didn't draw in. I should probably do that. The position vector r. Okay, so we've got this theta here. And recall that momentum is mass times velocity, right? So we have mass times velocity. And so we can rewrite our equation taking all of that geometry and stuff into account. L is equal to RP sine of theta. But again, P is equal to mass times velocity. So L is equal to R mv sine theta. Where again, pay special attention to where theta is. Theta is actually, you know, if I draw the line of action of R, again, I extend it out past the moon. That theta is going to be between the v vector and the extended position vector, the line of action. Okay. And so those are the equations that we end up with that are useful for us for angular momentum. And the idea is the same, right? The idea is the same as it was for momentum. It's literally a mass with a velocity. I mean, that's the way it's defined. It's a mass that has a velocity. Okay. It tells us how much. All right, so let's look at let's see. This is very confusing for me because I got a paper, the computer, and this is more confusing to me than what my normal setup looks like. So here we have an example. Do note something I didn't point out over here. So let me go back real quick. That this angle is usually going to be 90 degrees. All right, so that means sine is going to go to 1. So we're just going to end up with an L equal to RMV down here. So let's write that out as well. Just point that little fact out. Let's write that down real quick. I'll give you a minute. You need a bath, cat. Okay, so what is the orbital angular momentum of the moon? And it gives us the mass of the moon, right? So we have to take that into consideration. The mass of the moon is 7.36 times 10 to the 22nd kilograms. We have the radius, which is the distance from the Earth to the moon, okay? 385,000 kilometers. And then T is the period, is the time around the moon. It's how long it takes to travel one time around the whole moon. That's 2.36 times 10 to the 6th seconds. All right. So we're missing some information, right? Because if we look at our equation for L, all right, we have this mass that's going to be little m is going to equal to that big M there is going to equal to 7.36 times 10 to the 22nd kilograms. And we have the r, little r here is going to equal to big R of that 385,000 kilometers. All right, but we don't have V. So we have this one and we have this one, but we don't have V. So we need to find V. Okay. Again, we have the Earth. We have the moon's mass, M. We have this distance, R. Right, and this guy's going around the moon with some velocity, V, that we need to figure out. And if I extend out that line there, then I have this angle theta. But in this case, we know theta is going to be 90 degrees to that. Okay. So our equation here becomes L equals to MVR. So let's go ahead and let's find, that looks like a U. Let's find V. We had an equation. Did we do this? Yeah, we did. We did. Okay. We have an equation to find V. V is equal to, since it was a video, I didn't actually go through it, so my memory's not the same as it would be. So we have an equation for V equal to omega times R. So we're looking at, right, it's an angular velocity, omega. So we know the R. So if I can figure out omega, to find, I can barely see my screen. Give me a second. It's already all the way up. To figure out omega, if I can figure out omega, then I can figure out B. Okay. I was given the period T, so omega is equal to 2 pi over T. So that's going to be 2 pi over that time, which was 2.36 times 10 to the 6th seconds. I don't need the S there, but and so I've got omega of 2.66 times 10 to the negative 6 radians per second. All right, so I can use that omega to find V. V is going to equal to 2.66 times 10 to the negative 6 times 3.85 times 10 to the 8th. And that's just a quick conversion there. We had 3, 4, 5. I'm converting to meters. So that's going to equal to 1 kilometer is 1,000 meters. And so I get this out of the way real quick. That's going to give me 3.85 times 10 to the 8th meters. All right, so don't forget those conversions. There was a couple of the homework on, what was it? No, on the exam, because I just finished looking over the exam. That took me a lot longer than I thought it would. I apologize for that. But a lot of people, there was one question some of y'all got in particular where it was in milliseconds and y'all didn't convert properly from milliseconds to seconds. And by the way, on the exam, if there's anything, if you going over that, I believe you guys have access to see all the solutions that you put and what was right. If not, I'll make that change, but you should see it. If there's any problem that you think should have been counted right, don't hesitate to email me and I'll look at it. I'll see if you deserve those points. Perfectly okay with that. Sometimes there's mistakes. There was one in particular that one of y'all did that was counted wrong, but it should have been right, and I gave you points for that. 2.66. All right, so then just plug this in your calculator. It's kind of a weird segue. And you should get 1,024 meters per second. All right, so we have V, but that's not the final answer, right? We're looking for the orbital angular momentum of the moon. So we have an angle of 90 degrees. So this is just going to be MVR. So we just need to substitute in our values here. Wait. Yeah. The mass, and then let me rewrite this so it matches what I'm actually writing down. This is RMV. So that's R, that's M, and then V is 1024. Right, and sine of 90, we already discussed that at 90 degrees, that goes to 1, so we don't have to worry about that. So our final value here then is going to be 2.90 times 10 to the 24th, or 34th, sorry, 34 joule seconds. Right, so not too bad there. So any questions on that before I move to the next topic? Okay, let's see. Newton's second law of rotation, for rotation, right? Okay, okay, I'll check that out right after class. So Newton's second law for rotation. Most, going back again, most everyone did really okay on the exam. There's a few 50s, 60s, 70s. I think I got 1B. I didn't feel the need on this one to curve it because most of them were like 55, 50, 55, 56, 57 and up. So it rounded to about a 67 for the class. I didn't actually check that, so I'll make sure. But if let me check it real quick. Let's see. Let's okay for this. Let me check it real quick. Let me see what the average was. It won't take me long to do that. Ooh, it was lower than I thought. I might go ahead and round it a little bit. It gives us info on how good the questions are too. Most of these questions are good. It gives good information, so I'm not going to worry about that. But I might go ahead and round it up just a little bit. It's at a 54. I might round it up to a 60, 65, something like that. Okay. Newton's second law of rotation. So tau we saw, so this is coming again, this is going to be coming from our torque. Tau is going to be equal to, we saw, the derivative of L, our orbital angular momentum with respect to time, right? So we wrote it at like this, right? But that is L. Okay, so we wrote it like that. And so this is about equal to, right? If we wanted to go into more like a average orbital angular momentum, we want to think a little bit like that. It's about equal to the change in L over the change in time. All right, so we have tau equal to L2 minus L1 divided by the total change in time. Right, so we have that equation. Let me see where I'm trying to go with this. I don't remember. Okay. That's just some extra information. That's really not. I have that in my notes anyway. So the idea is here we're going to relate our torque to Newton's laws. So we've got dl over dt. This is the important part. Equal to d over dt times mvr sine of theta, right? But again, theta is going to usually be 90 degrees, so that's just going to go to 1. And so we end up with a dl over dt equal to d over dt, excuse me, mvr. And that's our tau, right? However, m and r are going to be constant, okay, for our purposes. M and r are constant. So whenever I'm looking at the moon orbiting the Earth, the fact is that r is not actually constant. The orbit of the moon around the Earth is not perfectly circular; it's more elliptical. However, the numbers that we get for our, especially for this class, it's close enough to the same r that we can just assume that r is constant. Okay, so m and r are constant. So that means that m and r can come out of that derivative. And we end up with, well, that doesn't look like anything. We end up with mr dv dt. And if you go way back, you should hopefully recognize that this guy right here is acceleration. All right, so tau is equal to mRA. And so the question becomes here, what acceleration is this? Is this tangential acceleration or is this the normal acceleration? All right, so if we're looking at the Earth and the moon, okay, again, we have this R, and the moon is traveling around the sun. We had velocity, and so we're the acceleration. So the question is, which acceleration are we looking at this point? Well, the acceleration that I care about, the acceleration that's actually changing the velocity's magnitude, that's going to have that effect on the torque, is going to be the tangential acceleration, AT. All right, so this is the one that we care about. All right, so looking at our equation again, we're going to have that tau is equal to mRAT. And we saw that AT is equal to R times alpha. So we can write this as tau is equal to mR times R alpha. So tau is mr squared alpha. And that I didn't write that down right. mr r squared alpha. You may or may not recognize this. We talked about this Monday or last time? Friday. This is moment of inertia. I. So tau is equal to I times alpha. All right. So where remember our Newton's second law, F was equal to mass times acceleration. Mass is, again, it tells us the more massive something is, the more difficult it is to make it start moving, right? So it's got inertia and it's due to that mass. Same idea over here with our torque. The more inertia, more moment of inertia there is, the bigger that is, the harder it is to get it to spin around or to orbit around something else, right? It's the more difficult it is to get something to spin around. All right, so we have that concept. We have the concept of how hard is it to make something move, and then we have the acceleration concept, except now it's angular acceleration, right? So this is Newton's second law for rotation. Right, where this was Newton's second law. And that was for translation, right? And again, translation just means it's moving left, right, up and down. We're not looking at spin. Rotation is actually when we're looking at spinning things or things that are orbiting around something else, something along those lines. So just as before we had a conservation of momentum, we also have conservation of angular momentum, right? And this occurs when no torque is present, when the sum of the torque is equal to 0. All right, so if no torque is present, oh gosh, feeling a little bit of, time is it? 30. I'm feeling some sprinkles. I might have to, we might finish this, do one more example problem and finish. Let me check. We'll see. We'll see what happens. If no torque is present, then angular momentum is conserved. All right, so then we have that tau is equal to dl over dt. Is equal to 0. Right, so then we can say that L2 minus L1 over the change of time is 0. Right, so I multiply both sides by delta t, and I'm going to end up with an L2 minus L1 equal to 0. So we have that L2 is equal to L1, and we're going to expand that to include the sum of all the particles in a body, right? So every particle in the body we can apply this to. And so we have, or if it's more than one thing orbiting around the sun or something like that, we have the sum of L2 is equal to the sum of L1. And so there we have conservation of angular momentum, right? And again, tau is going to equal to I alpha is going to equal to 0. Right, so here's the thing here is that inertia can't be 0. Moment of inertia can't be 0. Right? It's part of it. It defines a mass. right? It defines an object. It's one of the things that every object has to have, right? If inertia is zero, that means the object doesn't exist, right? It's the same idea for the mass. If the mass is equal to zero, well, then I don't have an object. I don't have a body. Okay. So I just put moment. The moment of inertia cannot be zero. Right. So what does that mean? And for this statement then to be true, for this statement here to be true, that tau equal to I alpha equal to zero, for that to be true, alpha must be zero. All right. So that means we do not have angular acceleration. Um, for, specifically for conservation of angular momentum. Just to point that out, that's for conservation of angular momentum. In order for angular momentum to be conserved, alpha must be zero. So alpha is equal to zero, and that means our omega is constant. It's not changing. Right? So conservation of angular momentum, alpha is equal to zero, omega is constant, and tau is equal to zero, right? I is not equal to zero. The moment of inertia can't be zero. Any questions? All right. So let's look at another example. Example 10. All right. I'll give you a minute to write that down. I'm going to go get some water real quick. Okay, so it says a 3 kilogram particle with V equal to 5I minus 6J meters per second is at X equal to 3 meters and Y equals to 8 meters. All right, so I'll deal with that information first. And I've already got the drawing here. But here's my object, right? Here's my particle. It's 3 kilogram particle. Yeah, you guys should see that right here. This little dot right here. And it says it's located at 3, 8. So it was 1, 2, 3, and then 1, 2, 3, 4, 5, 6, 7, 8. All right, so it's located that there. It says that it has a velocity of 5 I hat minus 6 J hat. So I did 5 I hat. So that's 1, 2, 3, 4, 5 minus 6 J hat. 1, 2, 3, 4, 4, 5, 6. All right, so that's where my velocity is going. That's what my velocity looks like. Yeah, I'm going to have to go inside after this, guys. It's sprinkling. And then the force is 6 I hat plus 16 J hat. It turned it into a capital J for some reason, but that should be lowercase. And so you do that. I'm going to have to go through this really quick. So 1, 2, 3, 4, 5, 6, and then 16. It went off the chart, so I kind of truncated there and just said it's more or less in that direction, right? So that's how the force is going. Let's rewrite these in vector notation. So I've got a 3 I hat plus 8 J hat meters. And then we had V is equal to 5 I hat minus 6 J hat meters per second. And then we had F is equal to 6 I hat plus 16 J hat newtons, right? So A, we want to find the particle's orbital momentum. So it's orbiting about this point O, okay? So A, we know L is equal to R cross P. I have the mass, I have the velocity. So I can figure that out. That's just a scalar multiplication of a vector. So that's going to be, what was it, 3 kilograms times the velocity, excuse me, which was up here, 5 I hat minus 6 J hat. So that's going to be 15 I hat minus 18 J hat. Kilogram meters per second squared. Kilogram meter per second. Okay. And then I can do the cross product. So L is equal to R, which was 3 I hat plus 8 J hat, crossed with P, which is 15 I hat minus 18 J hat. Doing the cross product, it's I, J, K. That's 3, 8, 0, 15, negative 18, and 0. All right. And so we're going to get, if I do I hat is going to be 0 minus 0, J hat's going to be 0 minus 0. And so our answer is going to be all in the K hat direction. It's going to be a negative 18. All right. So it's 3. Oh, why is it doing that? No, it's not negative. What's 3 times negative 18? I did it kind of differently in my notes. So let me see this. Oh, yeah. Let's see, we did 18 times 3. That's going to be negative 54. So that minus 8 times 15 is 120. And that's going to be in the K hat. Excuse me. So L is going to be, I got something really big, a lot bigger than I should have. Negative 1, no, let's see. That's negative 1, yeah, negative 174. I got the same thing. Make sure I didn't make a mistake. Negative 174 K hat joule seconds. Okay, that's our answer. B asked for torque acting on the particle. So we have tau is equal to the derivative of L with respect to time. So our L is actually constant. Right, so it's going to be 0. Right, our L in this case isn't dependent on time. It's going to be constant, so tau is 0. So that means that we are in a situation where we have conservation of angular momentum. And then C was, let's see, the rate at which angular momentum changes. Well, we just found that it's 0. Right, that's the change. It's about equal to dl over dt, and we found that to be 0. So that's our final answer there. All right. We got left. Yeah, let's end it there, guys. We've got spin momentum, orbital velocity, Kepler's law, third law, and then an example, a final example. So we'll stop there. Yeah, because I'm still getting sprinkles. I don't want to mess up this is my work computer. If this gets messed up, I'm gonna have to pay for it. I don't want to pay for it. All right, I'll see y'all on Friday. Yeah, I'll see y'all Friday. Got nothing else.
Take care, sir.
You too.